So in the next 2 minutes, I want you to obtain the permutation of the composite F composite G. F composite G, give me, once you have, of course, as you work out, the first row is normally the set, the second row are the answers. So what I'll be waiting for from the public chart is the answers you are getting for the second row. So obtain the results, the answers for this composite map, and give me the elements of the second row in that order. The second row is A, D, you can check, B, C. Now, if you compare these two permutations, this is what I wanted us now to use to show that the composition of permutations is not commutative. So compare these two permutations, GF, or rather G composite F and F composite G. To compare this, since the first row are just identical, it's the same set, you compare the second row. The first, for G composite F, the second row is D, B, A, C. In other words, that composition maps A to D. But F composite G maps A to A. It maps B to D, whereas G composite F maps B to B. So you can see the two compositions are not equal. The two are not equal. So we can say here clearly, G composite F is not equal to F composite G. So composition of permutations is not commutative. That's what we claimed in some remark before this example, that composition of permutations is not commutative. Another example, we can take this as number 2. I want us to use these two permutations, the ones we obtained from S3, where we had F4, F4 was 231, F6 was 312. Okay, anyway, let's say we have two permutations. I can still use F and G so that we don't tie ourselves to the listing we had made in the S3. So if F is the permutation 1, 2, 3, 2, 3, 1, and G, let's have another permutation G, 1, 2, 3, 3, 2, 1. Then I would like you to find F composite G and G composite F. So obtain those two composite maps. And then I would like us to compare and see if they are commutative. Are we able to show this lack of commutativity? So obtain F composite G and then obtain G composite F, and you compare the two permutations to check if they are commutative. So we can say here that so what we have found is that 1, you have found that F composite G is the permutation 1, 2, 3. 1, 2, 3, 1, 3, 2. And the permutation G composite F, you have found that to be 1, 2, 3. The second one was 2, 1, 3. So again here clearly we can say that therefore F composite G is not equal to G composite F. And that is in agreement with what we have said, that the symmetric group is not commutative. The symmetric group is not commutative, meaning that being a group, then it must obey all the other axioms of a group or all the other properties of a group except the commutative part. That is, you can show that it has the closure property. It obeys all the properties of a group. So I want to give you a question that I would like you to go and work on to show that S3 forms a group under the composite map. So this is an assignment. Remember last week I gave you an exercise to, we were working together on an exercise and then I was not able to post on the LMS as an assignment. So now I want you to write it down. I wanted us now to look at a different operation and prove the properties, the group axioms or the group properties. So the question is, show that this system S3 under the composite map forms a group, forms let me say a non-commutative. It forms a non-commutative group and the composite function. Under the composite function, it forms a commutative group. So I would like you to work on this. This is the first question. I will give you an additional question that will form your assignments so that when we will meet for sub-tutorial and arrange for a cut, then this assignment you will submit it. So have answered this question, keep it safe. Next week I'll add another question, keep it safe. When we meet in the face-to-face class, I'll require this assignment and then we will plan for a date to do a cut. Now, I think that's so much we have said about those groups or those algebraic systems that have just one binary operation. So a set and a binary operation. And remember, since these are algebraic structures we are introducing, they will be covered individually as a whole unit. So the second type of algebraic systems I would like us to mention is what we call a ring. And rings here fall in the category of those algebraic systems that consist of a set and two binary operations. A set and two binary operations. is also an algebraic structure, but now slightly different from the group, because the group carries only one, the set, and only one binary operation. The operation could be all the ones we have discussed. But now for a ring and a field, they carry the set and two binary operations. So let me see what is happening at the public chat. Now, why are we reducing and I want to introduce something new? Where are people? So anyway, we shall define a ring. We shall define a ring, and clearly, I think that's how much we shall do. We shall define a ring and then be able to continue in the next class. So I want us to define the concept of rings. I'll clear this. I hope you have written the question because I want to clear. So I'll clear that. So we want to introduce the concept of rings. And we want to define a ring. So let star and the dot be two binary operations. We want to define two binary operations of star and the dot. So let star and the dot be two binary operations of addition and multiplication, of addition and multiplication, respectively, over a non-empty set, over a non-empty set, say R. Then we can say that the algebraic system R and a star and the dot is a ring. It is a ring if the two binary operations satisfy the following conditions. Satisfy the following conditions. And the condition, there are several of them. So condition number one, I can continue up here. The first condition of a ring, we shall classify them. The first few ones are under, actually the first four are under addition, the star. So condition number 1 is that star obeys the associative law. Star obeys associative law, or the associative property in R. That is, associativity we defined as for every some element, say A, B, C in R, in the set R, then this is true, that A star B into brackets star C is equal to A star brackets B star C. So when you take any 3 elements of the set R, the associative property is satisfied. Condition number 2 is that there is an identity element with respect to star. So there exists an identity element say E, with respect to star. That is now depending on the binary operation with respect to star. There exists an identity element E with respect to star in R, in that set. That is, so the existence of identity here, it means that there exists E in R such that E star A is equal to A star E is equal to A for every A in R. So there exists an identity element E in R so that it acts on any element of R and leaves it unchanged. 3 is that each element A in R has an inverse in the same set. So each element A in R has an inverse say A inverse also in R. I hope you can now connect these to the properties we defined for a group, or we stated for a group. So each element in R has an inverse in the same set R. That is, you can have the implication here. That is, for each A in R, there exists A inverse also in R such that, that's what the property number 3 means, such that A star A inverse is equal to the identity element E. So for every element A in R, there exists A inverse in R such that A star A inverse is equal to the identity element. So with respect to the first binary operation, these four properties must be satisfied. Then property number 5 is that now with respect to the second binary operation, we can say that the second binary operation, which is now multiplication. The second binary operation of R also obeys the associative property. It obeys the associative law. That is, for every A, B, C in R, now this is the second operation. So A times B into brackets times C is equal to A times brackets B times C. So the second binary operation also obeys the associative property. 6 is what we called the left distributive law. So left distributive law, and the left distributive law states that now this is where you have both the addition and multiplication at play. So that multiplication, if I have A dot B star C, that is now multiplication and addition. Addition is the one in brackets. This is equal to, we normally say multiplication distributes over addition. So when you open the brackets here, you'll have A dot B star A dot C, like that. So for every, this is now, we can say here, for every A, B, C in R. So for every 3 elements, A, B, and C in R, multiplication distributes over addition. That is property number 6. And you see now the distribution here is from the left. So that's why we are calling it the left distributive law. But also the distribution could be from the right. So we could also have the same. We could also have the same, but now from the left, distributing from the left, from the right. So can say, I can even call this number 7, that the right distributive law, right distributive law is obeyed. That is, now I have, if I have B star, or rather let me just have them as A. So if I have A star B into brackets dot C, this means now I'm distributing my multiplication from the right. So I will have A dot C into bracket star B dot C. You can see here the C is multiplying from the left, from the right in both cases. This for every A, B, C in R. So we have the right and the left distributive property obeyed now by the two operations. So when we have a set with two binary operations and it obeys these 7 properties, or we would say 6 properties, then we say that this algebraic system is a ring. We call it a ring. And there are various sets that would satisfy, with two binary operations that would satisfy these conditions. Now I want you to compare the axioms or the properties we have stated for a ring, the very basic ones that we have stated for a ring. And since you remember the very basic properties we stated for a group, I would like you to tell me what is not compulsory for a ring. Which property is not compulsory for a ring and yet it is obeyed in a group? Which property is missing here very conspicuously? Because we have associative property, we have existence of identity element, we have existence of inverse element, we have star obeys the commutative law. This is the other property I had left out. That under star, the commutative property is satisfied under multiplication, under addition. So we can say that number 8, star, the binary operation star obeys the commutative law in R. It obeys the commutative law in R. That is, for every two elements, say A and B in R, A star B is also in R. For every two elements in R, their product, their sum, star is the addition, their sum is in R. So this is not commutative. For every two elements A and B in R, A star B is equal to B star A. So now look at those 8 properties of a ring that must be satisfied and tell me which property of a group is missing there. Which property of a group is missing? Now, does a ring require closure for the two axioms? Let me see if there's any response on the public chat. The numbers have gone down. So I can see a good number have fallen off. So it seems like we may have to stop there. But I'll pose this question to you. As you go down and assess or go through the properties of a group and the properties of a ring that must be satisfied. I would like you to find out, to compare and bring out some properties that are not mandatory or they are not compulsory for a set together with two binary operations to be called a ring. So we will stop there. I'll stop there, and let's continue in the next class. Unless there's a question.